Hello and welcome back. This is going to be video number 4 from chapter 18, and it's going to cover Friedel-Crafts acylation. So I have same learning objectives as video number 3. This will wrap out all of the problem set problems from chapter 18 through number 13 that you need to be able to do for exam number 2. So let's go ahead and get started with Friedel-Crafts acylation. So again, our benzene ring is our reactant. Let's see if we can get that. Okay. And here we have an acid chloride. Our catalyst is aluminum chloride. So acyl halides are extremely reactive, and maybe you saw them in 301, maybe you didn't, but we're going to make a benzylic carbonyl compound, benzylic carbonyl. So the carbonyl is at the benzylic position on the benzene ring. All right, so the mechanism for this reaction, let's take a look at what happens to generate the electrophile. Remember, we're talking about electrophilic aromatic substitution reactions. So I'm substituting this piece. So this is referred to as an acyl group, right? So the acyl group is substituting for a hydrogen on the benzene ring. Okay, so in the mechanism, in the first step, so to generate our electrophile here, we're going to meet a new type of electrophile. So our acyl halide is going to react with the catalyst, and in a similar fashion to what we saw before with Friedel-Crafts acylation. Okay, so we're going to form a complex to the catalyst. We're going to break this bond. And when that happens, notice that this piece, this carbon is going to be electron deficient. So here is our electrophile. Here I'm showing it as a carbocation. Here's the rest of, that's this piece here. Okay. And this is a resonance stabilized electrophile. So I can move a pair of non-bonding electrons that are on the oxygen and move it down to make a triple bond, so that we have here what's called an acylium ion. So this is a new type of ion. What's nice about acylium ions is that they do not rearrange. So it's resonance stabilized. This tends to be the biggest contributor, since here the oxygen and the carbon both have an octet, whereas here just the oxygen has an octet. Okay, but in either one of these, regardless of how you're looking at it, the carbon is feeling deficient of electrons. So even in this picture here, this is going to serve as our electrophile. So it doesn't matter which one of these hybrids you use as your electrophile, because they're both, look, they both have a +1 charge on them. And so you can either take this one and move it over here, and I'll just show you, it doesn't matter. Sometimes students like to use this resonance hybrid just as a reminder for where the attack happens, but I don't care which one of these you write down as. So our benzene ring, a pair of the pi electrons is going to attack the carbon, okay? So you can show it like this, or you can show it like this. I'll say or. Why does it not matter which one? Well, it's resonance stabilized, right? So the ion is a combination of these two, right? Okay. So now what do we have as our rhenium ion intermediate is what we should form next, right? So let's go ahead and use brackets. Don't stress out if you forget to use the brackets. You're not going to lose points for that. I'm just trying to highlight the fact that this is a reaction intermediate. We've lost this pi bond. And here, if this is attacking this carbon here, This has one lone pair on it, by the way. I'll go ahead and just draw it in case you forgot about it. And this is gonna move up here, okay? And if this attacks here, then our carbon is gonna have that octet, so I don't have to move any more electrons. Okay, so I'm just gonna go ahead and copy this piece down here. So I have, I'll use red. So I now have a carbonyl group. The carbon and the oxygen both have an octet, right? And now I better have a +1 charge, right? My +1 charge here is on this carbon. Here's my uranium ion. And by now, hopefully you can draw these resonance hybrids in your sleep. I'll let you do that for practice. And then in the next step, what happens is, let's see if I can draw in. I'm gonna just draw this in over here. Let's see, I'm gonna put in my hydrogen right here that's on this ring. We have the deprotonation step. So I'm gonna take my AlCl3, that minus charge. I'm gonna go ahead and deprotonate to form. So we've restored the aromaticity. And what do we have here? Oops, let's use red. And we get our product. If you drew this product on an exam and you didn't show the lone pairs here, that's fine. And then our inorganic byproduct is that, in this case, HCl, okay, which I don't care whether or not you show that to me. Okay, so let's go ahead and take a look at sort of the more examples from this reaction. So again, this is Friedel-Crafts acylation. So this is an acyl group here. And this is a great reaction because the intermediate here, our electrophile that's serving as our intermediate can't rearrange, which is not the case for Friedel-Crafts alkylation, right? So acylium ions do not rearrange. Okay. All right. So that's super nice. Another nice part about Friedel-Crafts acylation compared with alkylation is that we don't get polysubstitution occurring. And that's because the product is actually less reactive than benzene. And when we start in on the exam 3 material, you'll be able to explain why that's the case. So once we end up with our benzylic compound, or our benzylic carbonyl compound rather, which is what we had come up with just earlier, we can reduce it. And I like to use a reducing agent that is sort of friendly and easy to recognize, molecular hydrogen with palladium on charcoal as the catalyst to reduce it. In Klein, you'll see that he uses this zinc mercury with acid and heat. So this will do the same thing, and I think is a lot more obvious for students to say like, oh, we're gonna reduce, than looking at this. But you can give me either one of these, but this is what I tend to use, so you'll have to be able to recognize what I mean by that. So Friedel-Crafts acylation is a really nice way for us to put a really long chain on a benzene ring, because we don't have to worry about it rearranging like we do with Friedel-Crafts alkylation. So let's go ahead and look at an example of that. So here I have a 3 carbon and 4 carbon. So I've got 4 carbons here. Here's our acyl halide. And let's go ahead and predict the major organic product that we expect to make. So if I imagine, if I don't have to show the mechanism, which I'm not asking you for right now, if I imagine just ripping off this chlorine, I'm going to form a bond from this carbon to the benzene ring. So what is that going to look like? So now I have this carbon, which is a carbonyl carbon. And then I have my CH2, 2, CH3, okay? So here's my benzylic carbonyl compound. And then if I wanted to reduce this so that we had a 4-carbon chain, that's when I can do this hydrogenation. Let me just make this a little closer, okay? And here I'm gonna reduce this. So I still have this as this carbon, but I've reduced it now, and I still have these. Sorry, that looks a lot like a carbon. Just make that clearer. Okay, so I have 2, 3, 4, 5. So let me just see here. I've got 2, 3, 4. So let's. Did I make a mistake here? So 1, 2, no, I made a mistake counting. Okay, so 1, 2, 3, 4. So I just like to always notice how I just check to make sure that I haven't added or lost any carbons. That's kind of the most common mistake that students will make on an exam. So what's the name of this? So I have a 4-carbon straight chain attached to a benzene ring. So the benzene is the parent. So this is just butyl benzene. So I could ask you on an exam, come up with a 2-step synthesis to make butyl benzene from benzene, right? So this would be how you could do that. All right, let's take a look at an example of an intramolecular Friedel-Crafts acylation. So again, that was intramolecular Friedel-Crafts acylation. Okay, so I've gone ahead and wrapped this around, notice. So we can also use Friedel-Crafts acylation to make fused rings on a benzene. And the 5-membered and 6-membered rings are going to be the most stable. And if you're wondering, well, how do we know that this is going to end up here or here? Okay, you can do either one of those and not here or here or here. And it really has to do with stability. If you're making a 5-membered or a 6-membered ring that's fused to another, they're going to share, they're not going to go way out and then try to bond over here. Okay, so it'll just be here or here that you could attach this to. Okay, so let's go ahead and let's say that I want to see the intermediates for this, not just the products. Let's go ahead and do that. So hold on. Okay, so I'm going to imagine here, I'm going to go ahead and rip off this chlorine and have this be a plus charge. So I've got 1, 2, 3, and then I have this. Okay, and if you wanted to draw this with the carbon oxygen being a triple bond and the plus charge on the oxygen, that's fine. It reminds me of where the pi electrons from the ring are going to attack. I'm just going to use red so that you can see it, since this is all very close together here. So if I use this pair of electrons and attack here, then I'm going to end up with an uranium ion. So what is that uranium ion going to look like? So I still have this, I still have this. This is going to be a 1, 2, 3, 4, 5, 6-membered ring. Right? And I still have this carbon is right here, and I still have this oxygen. And then what do we have going on here? So there was 1 hydrogen here, and there was 1 hydrogen here. Okay. So I still have a hydrogen here, and I still have a hydrogen here. So where is the plus charge? Well, this has 4 bonds. This has 3, so this is where the carbocation is. And you should be able to draw 2 other resonance hybrids for this that are also uranium ions. Okay. All right, so this is where our carbocation is in what was a benzene ring. So this is our rhenium ion. We can draw two other resonance stabilized intermediates. And then in the next step, I'm going to see deprotonation. So let's think about where the deprotonation is going to occur so that we restore aromaticity. So we know we're going to make this. Here's our carbon, oxygen, double bond. Okay. How do we get from here to here? So if notice that there's still a hydrogen here, but there's not a hydrogen here. So let that guide you. So I'm going to go ahead and fill in my from Cl3 minus. Okay, so I'm going to use this bond, and if you wanted to take a non-bonding pair of electrons from the chlorine and then break this bond by giving that to the chlorine, that's fine as well. Actually, if you took this, let's see, 2, 3, 2, 4. Let me just do it this way, just while I'm thinking of it. I'm going to grab this and move this here, okay, so that I get that. And then if I wanted to reduce at the benzylic position, I'm going to do my hydrogenation, and then what will my product be here? Voila. Okay. All right. So we're going to have lots of fun doing this. Let's do some more practice. So when you're hydrogenating, just make sure that if you're hydrogenating at that benzylic position, the carbonyl at the benzylic position, and realize that I think I already mentioned that if you can also reduce a nitro group this way to an amino group. I mentioned that for how we make aniline by taking benzene and nitrating it and then reducing it. If the carbonyl group is not at the benzylic position, you're going to get no reaction. So this here is no reaction. So that carbonyl has to be at the benzylic position in order for this reduction to happen. So here, this reduction, and you can assume that this is in excess, is going to reduce both here and here. So what are we going to make? And if you just want to draw a circle in here, that's fine too. So that's your amino group. And then here, this is getting reduced to a CH2 followed by CH3. Okay. All right. And now what we're going to do is we're going to take a look at some guidelines for synthesis problems. And actually, before I get to the guidelines, let's just review some of the chapter 18 reactions that we've talked about so far. So this is, I do this a couple of different ways. I like to make tables and bubble charts, but it's helpful for you to play around with how to organize all the reactions, because this is just the beginning of sort of an explosion of reactions that's going to be happening in this class. So we've been talking about electrophilic aromatic substitution reactions. So you should be able to come up with just a generic scheme for that, which I've done here. This is also in your book. I went ahead and added in, since for almost all of these, they have catalysts. So if you want to include that, you can. If you don't want to include that, it's fine too. So we've talked about halogenation. These are the reagents. These are the catalysts that can be used. Here's the electrophile that is produced. Here's the organic product. So I've organized this then for nitration, and then for the sulfonation, right? And so now we can add in Friedel-Crafts alkylation and acylation. So I've left room at the bottom so that you can just try to fill in the table. See if you like making tables to organize reactions, or how I prefer to do it is to kind of make these bubble diagrams here. I think those are fun, so that I can really quickly go through and fill these in. Here is our Friedel-Crafts acylation. So, and then I can do my reduction. Right. And if you're wondering, like, why aren't you including the inorganic products? Well, I don't care about them. I just care about the organic products. If you want to include the inorganic products, that's going to help you learn it, then do that. So here, this is kind of my generic way to say Friedel-Craft alkylation. This isn't the only alkyl halide that you can use, but I just wanted to put in an example. Right, here I have my nitration. And then I know I can reduce that. Here's my sulfonation, and remember that's a reversible reaction. So I can remove that blocking group by just adding dilute sulfuric acid to go back to the benzene. So this is how I like to organize things, but also flashcards are also really helpful. I just like to see sort of everything at once. So yeah, anyway, you'll develop your own strategies for how you like to do it. So let's go over some synthesis guidelines. We're going to start to get into synthesis problems. If you're needing to put a long straight chain on a benzene ring, we can't do that with Friedel-Crafts alkylation. We have to use acylation. So we're going to acylate and then we can reduce. So for example, I could ask you on an exam to make propylbenzene from benzene. So let's go ahead and do that. So propylbenzene, 1, 2, 3, right? That's our propylbenzene. And if I'm going to have to acylate and reduce, so some people like to start from here and work backwards. If you want to pause the video and go ahead and do that, that's great. I'm going to start from here and I'm going to acylate, and I always like to write mine out like this. So this carbon is going to be this one. So that's 1, 2, 3, and I'm using as a catalyst aluminum chloride. And then I have my carbonyl group there, right? And then I can reduce. Okay. If you need to put an amine, so an amino group, on a benzene ring, what you need to do is nitrate and then reduce. So for that, let's practice by making aniline from benzene. So aniline, so this is where that naming is going to come in, right? I'm going to just name the compound, and you're going to have to be able to convert the name to the structure and then start at the beginning, benzene. So we have our nitration, so HNO3 with H2SO4. And I'm just drawing always the organic products here in the synthesis problems, because that's what we're going to be, isolating and using. And then I can reduce. Okay. All right, so that's fun. If we need to put a carboxyl group at the benzylic position, what we're going to do is go ahead and alkylate and then oxidize. So this one we actually did in the previous chapter, right? So you can use potassium permanganate or either sodium or potassium dichromate and acid. So let's go ahead and make benzoic acid from benzene. Okay, so benzoic acid has that carboxylate group, right? Directly bonded to the benzene ring. It's at the benzylic position. We're starting from benzene. So I'm going to alkylate and then oxidize. So I need to use an alkyl halide. If I want to use the simplest one around, I can do that with my catalyst. If I had wanted to do this with something like this, I could say CH3, sorry, squeeze that in there. You know, an alkyl halide that's a little bit bigger. I really wouldn't go, if I add a third carbon here, then I risk rearranging, right? Because this is a Friedel-Crafts alkylation. So that's why I'm keeping this small. And it doesn't matter how many carbons I'm using in my Friedel-Crafts alkylation, because when I oxidize, right, I'm going to chew off all of the carbons except for the one at the benzylic position. Okay, so I'm just going to do it using this for now. And then if you just want to write O in brackets, that's fine. I'm going to do my potassium permanganate followed with acid. Okay, and I get this. Okay, and so if I had done it using this, so I'll put down here or. So CH2, CH2, Cl, but then if I did this, I'd still get that, right? Okay, if you need to form a benzylic halide, you can alkylate or acylate, okay, either one of these. And then you can, if you acylate, you'll have to reduce. So acylate, then reduce, don't forget that piece. And then you can brominate. So we did this in the previous chapter with NBS, and you can either use peroxide or UV light. So for that, let's take a look at, let's say that we wanted to make, I don't know, let's do, we have a bromine at the benzylic position. Let's say that we wanted to make this from benzene, okay? So I'm gonna first do it the alkylation way, and then I'll do it the acylation way. So step one, from my benzene, if I wanna have a 2 carbon chain, so I'm gonna do this, CH2, CH3, and then the aluminum. Good, catalyst, and then I'm gonna make this, and then I can use NBS and either peroxide or UV light to brominate there. If on the other hand I wanted to do this by acylation, I'm going to have to add in that reducing step, but let's do that. AlCl3. So now I have this CH3. So now I have to reduce, and I end up with this. And then I can do my NBS with peroxide or UV light to get here, okay? All right, so make sure that you practice these synthesis problems. I think number 13 on the problem set has a bunch of synthesis problems. This is gonna be the end of exam 2 material, but keep in mind that all of the reactions that you've learned for exam 2 are still gonna be fair game on exam 3. We can't dump them out, we're gonna need them. So make sure that you're learning these reactions. Okay, stay tuned for more reactions, but there'll be reactions that you'll be responsible for on exam 3 and not just exam 2.